Hello and welcome to the monitoring episode of the International Society of Explosive Engineers web series, Explosives Every Day, which looks at how explosives are used in a wide range of applications. I'm Alistair Torrance, President of the ISWE. Our organisation started in 1974 when a group of like-minded people got together in Pittsburgh, Pennsylvania to discuss how to better apply commercial explosives and how to champion the blaster in the field. Move forward to today and we're an international organisation with more than 4,000 members spread over 90 countries with a mission to advance the science and art of explosive engineering worldwide. We do this through sharing our knowledge and providing training and education for everyone involved with blasting. We also have a strong education foundation and have awarded more than $1 million in scholarships to our students in our industry. Before we get started, I'd like to thank our series partners, Dyno Nobel, OPIT Blast and LDE Global. This series would not have been possible without their tremendous support. In this episode of Explosives Every Day, we take an in-depth technical look at monitoring for safety and compliance regulations. This will give you an insight into some of the more technical aspects that we have to use on a day-to-day basis and the mathematics and formulae that are tucked away behind the scenes to create a safe and effective blast. This episode sponsors are Sigicom and Aimone-Martin Associates, and here's a little bit more about them.
Sigicom is a Swedish multinational company that develops, manufactures, rents, and markets products used to monitor environmental parameters such as vibration, noise and air pressure, mainly to the professional end users. Several mega projects, as well as everyday users around the world, choose Sigicom's infrasystem to ensure that the environmental parameters of their projects are controlled, stored, and presented in the best possible way.
Aimone-Martin are leaders in the development of specialized instrumentation systems to measure off-site impacts of blasting and assist blasters with well-controlled blasts. Their goal is to help blasters do the work they need to do in an efficient and cost-effective manner. Aimone-Martin works in close association with their partners to provide you with a team of proven experts ready to assist blasters with the planning and execution of challenging blasting projects.
This episode's presenters are Chuck Dowding of Northwestern University, Cathy Aimone-Martin of Aimone-Martin Associates, and Johan Gjodvad of Sigicom AB. Professor Charles Dowding is co-author of a number of USBM publications which are the basis for blasting regulations in the United States. He is also known for his 4 books. He's a former member of the Board of Directors of the International Society of Explosive Engineers and a distinguished member of the American Society of Civil Engineers. Dr. Cathy Aimone-Martin is president of Aimone-Martin Associates in New Mexico. She served for 25 years as Professor of Mineral Engineering and is currently an Emeritus Professor with the New Mexico Institute of Mining and Technology. Cathy has over 40 years' experience in quarry and construction blast consulting and monitoring specialised in close-in blasting effects on, above and below ground structures. Dr. Aimone-Martin is the author of over 87 publications and regularly conducts training courses for blaster certification in 11 states. Johan Gjodvad is a Strategic Partnership Manager at Sigicom, where his focus is innovation and the international market. His work ensures Sigicom continues to be a top innovative producer of hardware and software for environmental monitoring. Johan has extensive experience on environmental impacts like vibration, noise and dust from various sources, blasting during civil works and demolition using explosives. He has been part of the Danish Federation of Explosive Engineers since 2006 and is past president of the European Federation of Explosive Engineers. Chuck, Cathy and Johan will break down the technical aspects of monitoring, the use of monitoring in real life, and as well as a comparison of international standards. There's going to be a question and answer session with the presenters right after this presentations. The panel will discuss many questions that were asked by a live audience at the time of this episode's first airing.
This tag team presentation will begin with a graphical portrayal of the many levels of monitoring. We start at the lowest level, data, a single point. Did the peak particle velocity and/or time history of the blast satisfy a criterion? Quality of that data is heavily dependent upon seismograph placement, which is in turn dependent upon the training of the seismograph operator. Moving up to the second level, information, involves a second data point that allows drawing of straight lines. Most often seen are scale distance plots employed by blasters to describe influences of geology and constraint on expected peak particle velocity. Dr. Aimone will be presenting case studies of various uses of scale distance plots. 3 data points allows construction of nonlinear relations and introduces a third level, knowledge. The Z-curve relation between dominant frequency and allowable peak particle velocity is such an example. Seismograph manufacturers are important stakeholders because they provide software to determine dominant frequency of time histories of the measured ground motions. The next level, wisdom, involves knowing how measurements compare with appropriate criteria. For example, comparison of allowable strains with those calculated from measured structural response. Project consultants are most often involved in these determinations of critical strains. Finally, regulations need to be considered, and as shown, are not always consistent with physics-based criteria, for they are the rules by which the governing authority operates. An example might be the difference between a regulation based upon annoyance instead of cosmetic cracking. Johan Gjodvad will discuss the project to compare regulations around the world. This rubber band model of the structure on the left demonstrates the importance of frequency in addition to peak particle velocity. Most important is the ratio of dominant excitation F sub G to the natural frequency of the structure F sub S. This drawing shows that the cup is analogous to the mass of the structure. The stretch or strain of the rubber band is analogous to the strain in the walls of the structure, and the motion of my hand is analogous to the ground vibration motion. So watch this movie while I take a rest. This simple dynamic system responds at its natural frequency when excited with a single pulse. If it's excited with a high frequency, little stretch in the rubber band occurs. Also, if it's excited at a low frequency, there is little stretch in the rubber band. However, when excited at its natural frequency, the system's response is maximized. This response and stretch in the rubber band is equivalent to the strain, which causes cosmetic cracking. Knowledge and dominant frequency. The movie showed that the largest strain in the rubber band occurred when the system was excited at its natural frequency. The question then becomes, is the amplitude of the ground motion of the blast in the upper left of this drawing large enough and close enough to the natural frequency of the structure to cause cosmetic cracking? Current regulations based upon the observation of cracking by the U.S. Bureau of Mines are described by the Z-curve In the lower left set of graphs of allowable peak particle velocity as a function of the dominant excitation frequency. The Z-curve restricts peak particle velocities to their lowest values for ground motions whose dominant frequencies are below 10 Hz because the residential and similar commercial structures have natural frequencies of 5 to 10 Hz. So what are the amplitude and dominant frequency of this ground motion to be employed in the comparison with the Z-curve? There are two possible approaches if only ground motions are measured: the zero crossing pulse and the fast Fourier transform analysis. The zero crossing pair of amplitude and frequency are plotted as x's on the lower left. As shown in the upper right, they are the amplitude and frequency, which is equal to 2 times 1/2 the period t, associated with each pulse shown in the upper right. This example shows that one of the transverse pulses here exceeds the lower limb of the Z-curve for plaster walls. This conclusion is verified by the FFT on the lower right, which shows that the dominant frequency of the time history is 8 Hz, which is the frequency of the pulse that exceeds the Z-curve. Wisdom and wall strains and crack response. Measurement of structural response and crack response of this concrete masonry unit house demonstrate the power of additional monitoring. Differences of vibratory displacements at positions D4 and D2 shown in the line drawing can be employed to calculate wall strains. The micrometer displacement gauge across the crack and the front wall allows long-term climatologically induced changes in crack width to be compared to those induced by blasting vibrations. Time-correlated top right 2 displacement time histories were subtracted to produce the orange relative displacement time history. As shown by the inset, division of the maximum relative displacement delta by the wall height h gives the shear strain in the wall. Comparison of the orange strain time history with that of the crack response time history shows that they are remarkably similar. Comparison of the long-term crack response in dark blue with the vibratory response in the black bars for the case history just described shows that daily changes in temperature in pink produce crack responses that is 2 times larger than that produced by blasting vibrations that exceed 0.5 inches per second. Furthermore, cracks open and close even more with the changing seasons of the year. For more response on this and other case histories, please see my book on micrometer crack response. Blast-induced strains can also be directly measured, as was done to allow blast fragmentation of the Manhattan schist immediately below New York City's Grand Central Terminal, shown here. The next slide will show how the strains were measured in the columns, encapsulated in red here, supporting both the train shed and the large buildings immediately above Grand Central Terminal. During the blasting for ventilation shaft number 5 here that occurred within tens of feet of the column foundations. Column strains were directly and indirectly measured. Direct measurements were made with foil gauges glued to the steel after the fire-protecting concrete was chipped away. Indirect measurements were made by measuring the velocity response time histories at the top and bottom of the columns. In a manner similar to that employed in the residential structure, the strains were calculated by dividing the time-synchronized differences between the upper and lower displacement by the distances between the upper and lower velocity transducers. Comparison of the directly measured and calculated strains in the green is even more remarkable than in the previous comparison. Correspondence of the frequencies and timing of the peak pulses is good. The amplitudes differ. Oh, how far the monitoring and instrumentation have come. All of the instruments here I needed to record time histories in the early 1970s have been reduced to the size of a brick in the lower right, with no moving parts. Soon they will be reduced to the size of a deck of playing cards, the volume of which is occupied mostly by batteries. If this battery problem can be solved, the seismographs could shrink to the size of a quarter in the 2030s. Thank you very much for paying attention to my presentation. There are two important things to take away from this presentation. The first is that the response of structures and the subsurface is a function of the strain induced by the passing of the ground motions that we commonly call blasting vibrations. The second is that my publications are available in PDF form for downloading for free from this website shown here on the slide.
Hi, I'm Dr. Cathy. I serve as a blasting consultant on many close-in and challenging rock blasting projects in construction and mining. I will discuss vibration monitoring and the use of seismographs placed close into blasts to compare the response of ground vibrations for different explosives and powder factors, time delay systems and timing, and illustrate best practices when responding to structure damage claims. We will focus on the attenuation model shown here in the upper left, where vibration measurements in terms of peak particle velocity are plotted against corresponding distances scaled with explosive charge weights. This model will serve as a graphical tool to help explain the performance of rock blasting, guide us with modifications to blast designs, and to predict vibrations at scale distance values not represented by measurements. The models shown here with two straight lines represent measurements from 22 blasts where seismographs were deployed in linear arrays, shown in the upper right, over 3 orders of magnitude on the scale distance axis. One line is the median or 50 percentile with a y-intercept at scale distance equal to 1, or what we refer to as a k-factor of 38.9. The slope is minus 1.24 and is indicative of the weathered granite we're blasting here. The coefficient of determination, or r squared, describes how well measurements fit the median or 50 percentile trend line. The 90% r squared shown here is considered to be very good. The upper black dashed line, drawn at the same slope as the median line, is placed coincident with the highest measurements. This upper bound with a k-intercept of 83.9 represents the highest possible or worst case peak particle velocities for well-behaved measurements. Many monitoring specialists will use a 95 percentile line, shown here as the red line, as the worst case, assuming 5% of the data are outliers and can be excluded. I will now present a few case examples using attenuation models to evaluate blast performance and to modify blast designs. Explosive performance for trench blasting are compared in these videos. ANFO delayed gas pressures shown here create excessive vertical rock motions at 25 Hz dominant frequencies, and the disturbance of the rock is well outside the trench perimeter. Close-in vertical ground displacements and attenuation rate, shown in the attenuation model to the left, are indicative of gas forces lifting the rock outside the trench parameter. Using dynamite, the blast shown to the right, one can clearly observe the detonation wave associated with very little ground disturbance outside the trench parameter. 65 Hz peak frequencies dominate, and the more brisant explosives result in a far faster attenuation of vertical displacements outside the trench, shown with the model in the red symbols. This attenuation modeling example for a Western coal mine shows a K-factor of 57.2 inches per second, using an extremely fast 8 millisecond down row delay timing. Fragmentation was poor, blast holes at the end of the shot were sympathetically detonating, and backbreaking ascended up to 127 feet behind new high walls. Heavy orange smoke, byproduct, or NOx resulted, indicating blasting agents were detonating under less than ideal conditions. OSM regulators mandated the elimination of NOx, based on complaints by residents that the smoke was poisonous. Using high-speed photography and pressure sensors inserted between boreholes, we determined that excessive ground stresses were prematurely shattering the emulsion microballoon sensitizers based on microscope analysis of emulsion samples. Signature hole analysis indicated an ideal down row timing of 27 milliseconds. That resulted in reduced model y-intercept of 17 inches per second. Fragmentation improved, backbreak was controlled to 38 feet, and NOx was virtually eliminated by preventing deflagration by slowing down the delay timing. Several blasts were performed at this limestone quarry to compare the performance of 3 initiation systems that included det cord delayed by row, non-electric pyrotechnic delays, and electronic delays. Fragmentation was characterized using split software, and attenuation models for the 3 systems are compared in the lower left-hand corner. A power draw meter was placed in line at the electric meter station to continuously record primary crusher power consumption for each staged blast using a unique delay system. Comparisons were dramatic. The cumulative fragmentation size distribution plot in the upper right-hand corner shows electronic delays in the red symbols produce the smallest fragmentation size at the 80% passing. Crusher power consumption for electronic delays, plotted in the lower right in red, indicated an average reduction in crushing energy of 57% using precise electronic dets compared with the det cord system. The attenuation models for representative shots in the lower left show a significant reduction in the y-intercept using electronics, signifying a better utilization of explosive energy in the breakage process, reduced backbreak, and less wasted energy propagating as ground motions. The case of this Florida quarry is one of undershooting and wasting explosive energy. The quarry moved blasting operations from the northeast area to the southwest area and closer to inhabited structures. Electronic delayed blasting typically was performed with a powder factor of 0.2 pounds per cubic yard. The attenuation model provided a slope of -1.4 and an acceptable R-squared of 84%. In the southwest area, 4 decks of 100 pounds per delay were required to meet vibration limits. Beyond a scale distance of 10, peak particle velocity amplitudes were far higher than expected, and the model exhibited a slower attenuation rate at -1.26. After 5 blasts, we realized that we had cut our powder factor in half, and we were undershooting the rock, resulting in wasted energy. We adjusted the loading at a powder factor of 0.18 with 350 pounds per delay, and the attenuation fit in red exactly hit the 80th percentile line of the original model. Vibrations at the closest structure plotted right on the U.S. Bureau of Mines safe limit. The owners of the house outlined in yellow in the upper left photo initiated litigation against the nearby quarry to the north. The house sits within 50 square mile area of documented slope instability and shallow landslide susceptibility. The claimant believes blasting damaged the home and claimed loss of value subsequent to a home sale, although no visible cracking in the house exists. Landscaping and asphalt drive show evidence of significant downslope soil creep toward the river to the south. Seismographs were placed at the road 220 feet away from the house by the blaster, consistently generating PPV under 0.75 shown in the lower left. However, these amplitudes ranged in frequency between 2 and 15 Hertz, matching the natural frequencies of structures, as Dr. Dowding demonstrated with his bouncing cup. This frequency matching contributed to amplified structure motions and undoubtedly perceived by the inhabitants as damaging. The site attenuation model shown to the right, using records supplied by the blaster, resulted in an unacceptable regression correlation coefficient of 36% and a median y-intercept of only 3.9 inches per second, which is far too low for igneous rock. Such a model could not be used in the litigation case. We subsequently developed a more representative model and compared with the blaster's model here in red. Data correlated perfectly, we now have a reliable model to predict worst case, highest possible ground motions at the claimant's structure to refute this claim. In these examples, we have used site-specific ground motion attenuation models to explain and improve blasting performance. Such modeling can be extended beyond ground velocity using sophisticated seismographs with 8 channels and sample rates up to 128K. Breakout boxes can integrate seismographs with a variety of displacement, velocity, acceleration, and pressure sensors for a wealth of instrumentation demands in the air, underwater, and on structures as well as in the ground. As Dr. Dowding suggests, the future of instrumentation may be limited only by our imagination. I thank you for your attention.
Hi everybody, this is Johan talking to you from Scandinavia in Northern Europe on the other side of the big pond. I'm honored to talk to you about monitoring, which is a very important part of blasting. This as it both protects structures and individuals against the effects of explosives, but also ensures that the blasting work is optimized to give the best possible result for the blaster and the company and economy in it. You've had the pleasure of having good introduction into vibration monitoring by Professor Dowding, one of the leading experts in the world, as well as good examples from another expert, Professor Aimone-Martin. I really hope you enjoyed these presentations as much as I did. Now, I would like to talk about the differences between monitoring standards around the world. There are several different standards around the world. Some have their own, some look to other standards, some are determined by law, some are voluntary, and several places things are just done because they were done so last time. Together with my colleague from the European Federation of Explosive Engineers, Mr. Matthias Jan, IFE, or the European Federation, is equivalent to ISEE, just a lot smaller. We knew that apart from having different standards, their boundaries were also different. Therefore, we initially made a survey to see the differences. The survey confirmed the differences. The major differences between standards is whether the standard take frequency into account. Most countries include frequencies, meaning that a higher frequency allows a higher PPV. In a few countries, the PPV value depends on the distance and on the underground. And then there is a third kind where the PPV value is dependent on other parameters. USA, of course, includes frequency and is one of the oldest and most well-documented standards or criteria for safe limits of PPV. Another difference is which components or directions that are considered. As you see in orange, most countries make use of the peak component particle velocity to determine the allowed limit. This includes the US, and it basically means that the largest components of the 3 axes. A few countries make a sum of the components, as you can see in green, and 2, Sweden and Norway, only considers the vertical components. I could explain you why I believe that is the case. And a single country or standard makes use of the horizontal component. Here's a graph showing some of the major standards which are including frequency. The vertical axis shows velocity, while the horizontal shows PPV. Here it is well illustrated how PPVs with lower frequencies are considered more dangerous. There are different graphs depending on what type of house or structure that is considered, of course. In this case, the standards are for residential houses or similar. Other categories could be fragile historical buildings or office buildings and so forth. And there is, of course, completely different rules for tougher installations such as harbors, roads, etc. As you saw on the previous slide, this type of standard based on frequency is the most common. The red graph in the top is the USBM. It seems like the most lenient of the standards, allowing the highest values. However, it is also the standard we have found to be best documented, why it can defend the allowed high values. Here, an overview of standards that depends on distance and the type of ground material under the structure. In principle, lower levels of vibration are allowed at longer distances and softer underground. Here's a slide to summarize on the findings of the first part of our comparisons of standards. There is a big difference in what is accepted by the different standards. In some cases, we identified a difference in allowed PPV with a factor 3 for the exact same scenarios. I haven't elaborated on this, but believe me, it's true. Some of the standards consider 3 axes and some only consider 1. Frequencies are considered in some standards and others do not. Distance and/or media is included for some, others do not. Positioning is different. It can be dug down, as they do in the US. It can be placed on the foundation, and some actually place additional seismographs on the top floor. And there is national standards by law, and some just refer to other national standards, and some just do business as usual without actually knowing why. Why is there this difference? Well, in our project we needed an explanation. Therefore we set out to make a second phase of the project. Of course we've been a bit delayed by the COVID pandemic and how the world looks because of that, but we aim to start monitoring as of March 2021. So basically while you're looking at it, I'll probably be on my way soon to the site. Well, the idea is to physically compare the different standards and to challenge them and see the difference in a live project. We have been lucky to get access to the largest open pit mine in Europe, the ISEE mine, north of the polar circle, which blasts all year round. It's very close to Santa Claus, I should tell you. We have been given access to install equipment on the buildings, and we have actually already made our first site visit and installed equipment which is monitoring as we're speaking. We cooperate with a local technical university, Luleå Technical University, on the project and have gotten a master student from them who is going to write his thesis based on the data and the things we're looking at, which is actually also to compare standards. Just to show you the size of the ISEE mine, the red circle on the wall behind me on the left picture is the dumper shown in the picture on the right side. I'm standing next to the wheel of this 297-ton dumper, and I'm about 190 centimeters, which is approximately 6 feet 2. So big production. Here's a cross-section and overview of the planned monitoring equipment. There will be vibration monitoring in the bottom of the pit, on a service building down there. There will be vibration monitoring at the first structure coming out of the pit. And finally, there will be several vibration, crack and air blast sensors on the first building, which resembles a residential house. This final slide shows how the equipment is thought to be mounted. The first vibration monitoring position is on the ground, which is to resemble US practice. The second on the bottom of the foundation is according to Germans and several other standards. The third on the top of the building is to be able to calculate global shear strain, which is also the case for the fourth position protected by the ladder. The orange square approximately indicates where we will install crack gauges to monitor crack. Crack monitoring was introduced by Professor Dowding in one of the previous presentations. And on this project, Professor Dowding also ensures that crack monitoring is done the best possible way. The blue circle indicates where we will install an air blast microphone or air overpressure microphone to be able to record changes in pressure originating from the blast. I can assure you that in this blast there will be no high values, but we still need to monitor it. Finally, it's important for me to stress that monitoring is closely connected to what has always been a key issue for the world of explosives, namely safety and health. This both for our colleagues, but also third parties like people living nearby, nature or animal life. We care about our surroundings. Blasting is great fun, and so is monitoring, but in our daily work as professionals, we take great care both to optimize but also to protect ourselves and our surroundings. And as technology enhances, we can work closely to the limit, optimizing the production, but also at the same time ensuring the safety of our surroundings.
Well, I think the presenters did a great job on showing how technical our industry can be. Our question and answer session with moderator Travis Davis-Haver, ISEE board member and emerging professionals section chairperson, begins now. So take it away, Travis.
Thanks again, Alistair. And again, without our sponsors, we would not be able to bring this free webinar series to you. Now let's talk with our panelists. Chuck, who's in Illinois, Cathy in New Mexico, and Johan, who's in Denmark, where it's pretty darn early in the morning. They're all here ready to answer your questions. So please send your questions in via the question and answer box, and we'll have those forwarded off to our panelists here this evening. Our first question is for Chuck and Cathy, and it comes from Mike Mann. What motivates you both to continue providing your expertise after so many decades of service?
Well, it's really important to transfer the knowledge to the next generation. I'm always excited about meeting younger people and helping them get a leg up on this great profession that we have. I've also discovered that I thought once you did something, it never needed to be done again. But I found out that every generation needs to start again and learn from the beginning.
I think in my case, the camaraderie that I enjoy in the field is something that motivates me. We're all out there at 4 o'clock in the morning, 3 o'clock in the morning, and getting ready for the blast, and we're all working for the same objective and same goal. And I think just all of us out there working, getting dirty, it's just a great union and fellowship, if you will. And the other one is seeing the fruits of our labor. There are many jobs that I've worked on and have worked out in the field and worked very hard to get the rock excavation going and the foundation going. And then a year later, I can come back and see the high rise in New York City or the new bridge over a river. I think seeing the fruits of your labor is very, very motivating.
All right. So our next question, I think we'll start with Johan. What are the most strict vibration and air blast regulations?
What are the most strict? Yeah, well, you know, it's not easy, but you could say perhaps the German standard. And if I don't know if that's the answer, it answers enough, because there's also reasons for this, because the Germans, I have to be diplomatic here, they would argue that they have a lot of more old buildings and structures they need to take care of. And I don't want to get into the discussion, but some of the standards are based on annoyance and perception rather than the structure. So yeah, it's also how you approach it and see it, because you could also say the Nordic from the Scandinavian standards are also quite strict if how they're treated, but they don't include frequency like we do. So it's not easy to just put them up on like 100-meter run like the Olympics. It's more complex than that. But I would say the German.
So Chuck and Cathy, what about in the US? What are you seeing as some of the most stringent requirements for air blast and ground vibration?
Well, there have been initiatives by some local authorities to try and reduce the Bureau of Mine standards adopted by the Office of Surface Mining. That's been particularly problematic with regard to issues in the United States. However,
I think,
yeah.
Go ahead.
No, go ahead.
Yeah, I was going to say, in my case, oftentimes we see projects where the standards are much lower than the Bureau of Mine standards. Mm-hmm. And oftentimes they are low enough to the level of perception. And oftentimes that perception level, which is sometimes 2 or 3 orders of magnitude lower than what might cause distress to structures, are there to prevent complaints and to mitigate complaints that might stop the job.
Well, one of the challenges, I think, is that humans are so much more responsive to vibrations than our structures. What is startling to a person is not necessarily startling to a structure. That's why, you know, I've been very interested in monitoring the response of cracks in homes to changes in temperature and humidity. And we found that homes respond far greater to changes in temperature and humidity than they do to ground motions generated at the regulatory levels. So one of the biggest challenges we have is that humans, because, you know, the world revolves around us. We're the humans. If something bothers us, it must bother everything else. And this is a big sociological challenge that we have in our industry.
And there's also studies that shows that if you have noise combined with, you will feel the vibrations earlier because you're suddenly aware of the, let's say it's a groundwork outside and you can hear it, suddenly you can feel it, and you're aware of everything. And so human annoyance is is much lower, and therefore you detect it earlier.
One of the challenges is the ground motion propagates at a higher velocity than the air pressure waves do, the air overpressure. So when you have a large air overpressure wave, first comes a vibration, then comes the air overpressure wave that then excites the home and you hear the dishes rattle. So it's actually, you think it's much longer than it really is. So there are some big human response challenges that we face.
But I also want to point out that of course blasters and the consultants and the equipment, we do consider that some places we have to take more care. If we're close to schools, if we're close to fragile structures, we do take more care, and that's why we're here. That's why this is even a business. Is because we do take care of our surroundings. I have to stress that.
Our next question comes from Spencer, and Spencer would like to know if there have been any studies or experience of high explosives versus deflagrating explosives to resolve vibration issues.
We've done that.
You had an example, did you?
Yeah, we've done that in Henderson, Nevada. We compared high explosives to deflagrating explosives, and it did make a difference. And we made sure that after, I think Chuck was there also, weren't you, Chuck? And we made sure that we excavated afterwards. Of course, we didn't have the same fragmentation. We certainly had lower vibrations, but we had coarser fragmentation with the deflagrating. But it gave us the same crater shape. We just used one hole, and it gave us the same shape, same size of the excavation, but it was just more difficult digging.
Okay.
I know there is companies that control the size of the fragmentations simply by knowing the vibration level, and then they can design the blast afterwards. Yeah.
Our next question here is for Johan, and I think, Johan, it comes back to a statement earlier. The question is, in Germany, how can blasting be done economically with such stringent limits?
Ooh, Germany's our southern border. We had issues with them before. I should take care of what I'm saying here, but they do monitor, and they, I don't know, but they do work around it. And I would say, on the other hand, there's not so much tradition in monitoring like there is other places, but when they do, they do manage to do it. And the German standard, you have to remember, is not only for blasting, it's also for all kind of other things. It includes the whole lot. So, but I'm not going to answer politically why they do it, but I can tell they do manage to use them. So.
All right. Our next question is for all of you on the panel, and it's from Dennis. Do you worry about air reflection in having air pressure monitoring devices attached directly to walls?
That's a good question. That's a good question.
I think the approach used by David Siskin in his landmark studies was to actually have the transducers approximately 2 or 3 meters from the structure, on the side of the structure, facing the blast. So you want to get the incoming air overpressure wave, and you want to be in such a way you don't get the reflected wave. What you find is that the air overpressure wave takes a while to get across the structure, and so you actually have competing air overpressure pulses acting on the structure.
And most standards also have a compensation for that, saying if you're on the wall, you have to do so and such.
Actually, Cisco never did find a crack associated with air overpressure. So the air overpressure regulations are really far more conservative than even the ground motion regulations.
All right, our next question is for Cathy. And Cathy, in your diagrams, you indicated you had a red line that was indicating an attenuation for the site. How did you establish that, or how did you determine it? Did you do it through additional monitoring or reanalysis of the original data?
Are we talking about for the quarry?
I believe so.
Yeah, I think for the quarry where, oh, yes, I neglected to explain that we had taken seismographs. We put out about 15 seismographs in an attenuation line at varying scale distances. We like to put those scale distances at doubling increments. Say the first one would be 10, the next one would be 20, and then 40 and 80 and so forth. So to accommodate the power function of the way vibrations propagate in the ground. And then as many as we can, and it gives us a nice straight line. Make sure we bury the geophones very well coupled in the ground, and we got almost a perfect correlation with the one blast. And so
I want to emphasize what Cathy said. It's far better to monitor one blast with multiple transducers rather than multiple blasts with one transducer, because you cannot take into account the variations in the spacing and burden and errors in the timing. So it's very important to do what Cathy.
And it's also it's very hard to replicate it from place to place. So you have to do it on the place you're on. I actually know a company that's been working for more than 30 years, and they collect the data from previous blasts. So if they ever come back to that town, to that specific street, they include that data for making the prediction.
Very good. Very good.
Yeah.
All right, our next question here is from Frederick, and he's asking for some advice on how to explain to a community that might be complaining about cracks and noise, even when the monitoring is indicating that the vibrations are producing intensities that are much less than that of a threshold or criteria limit.
Well, that's one of the reasons that I've been pushing this crack monitoring device, in that you can demonstrate to people that the cracks in their homes actually expand and contract just due to changes in temperature and humidity. And when you think they're observing cracks developed by the ground motion, the cracks are actually being produced by changes in temperature and humidity that are really extreme. And I think that's another way of focusing on the issue rather than the measurement of the ground motion. It's another way of communicating. I'm sure there are other techniques, so Cathy, you probably have some good sociological things that have been done to help communicate.
no, I share in the enthusiasm for crack gauges because I think they're very telling, and to get the homeowners involved in that scientific experiment, if you will, is very important. I think also human activities, opening and closing doors, children running through. I mean, they can see this. We put the monitor at the corners of the house. They can actually see what the vibrations are relative to a blast. And oftentimes it's orders of magnitudes more. And then they shake their head and yes, they agree.
Mm-hmm. I had, sorry, go ahead. Travis. No, I had my first boss, like real boss in real life, was said there's three types of people in this monitoring. He said there's one type who's like who just want to have a new a repair to his building, and there's the other type which is suddenly aware of everything, and then he sees all the cracks that were there already. And then there's the third type that actually has cracks. And with all those three types of people, you actually cover with the monitoring and probably documentation as well. But you have to know that there is all those three types.
Yeah, I think that brings up a really important point. Never blast without a seismograph on the site, because right. Humans are going to respond, or you better have a scientific way of defending yourself. Just, well, here's exactly what happened, not what people thought. So a lot of the cases that I've had where people have run into difficulties when they have not had sufficient number of seismographs on the site to actually demonstrate what the ground motion and the air pressure levels do.
Our next question is for all of you, and it comes from Eric. And he's asking, what are options available to blasters to help control vibration?
Well, the most important one is to use electronic detonators, because then you actually detonate exactly what you plan. That I think is the most important development that we've had in the last 10 years for controlling ground motions. There are others. I'll let the others add a few.
I mean, you don't want to get into the details, but delays are very good to lower the vibration level. Like if you have delays on the blast, it lowers the level of the wave. Cathy?
Well, I agree with Chuck, and I think that's very important because I think most of our studies on vibration and controlling vibrations have to do with frequencies and delays. Electronic detonators are by far the easiest to control frequencies and to make sure the precise timing then mitigates any kind of overlaps with vibrations for individual holes. And I think signature hole analysis can tell us exactly what the natural frequency of the ground is, and we can offset that natural frequency with timing so that we don't get resonance or enhancements at the houses. And it works 100% of the time.
There are blast design techniques that can be employed to reduce the amount of ground motion per unit fragmentation. For instance, a lot of people don't talk about this, but what I call sort of drill factor. How many linear feet of holes do you have drilled per cubic yard? And in other words, you distribute the explosives within the fragmented volume, and therefore improve the fragmentation. So you use when you keep the powder factor constant, it's good to have a high drill factor as well.
I found in my own practice as a consulting engineer that there's a lot of push to use less explosives or just simply make the shot smaller, and that can work to some degree, but undershooting the rock actually produces significantly greater vibration because the energy is not going into breaking the rock. It's
you can use smaller detonators per delay, but you have to keep the powder factor constant. You have to be careful. There's a lot of design parameters to keep in mind.
All right, I think we're down to probably our last question or two here for our panel. And this question comes from Alan. And the question I'll just shorten up by asking, when do you find people are making complaints or identifying issues with blasting? Is there any part of the day when they're potentially getting up, when they're around? What do you see in your daily experience?
It's a good question. That's a very good question. I think the best time, of course, is at noon. A lot of blasters in cities with construction blasting would like to shoot at noon because people are not in their homes, they're out traveling or not at their businesses or in their cars or walking around. 3 o'clock in the afternoon is also a good time, but I think some of the worst time, of course, are people who sleep during the day, they work during the night, and so that's very difficult. Whenever the weather is favorable, noon to 3 o'clock is some of my favorite times for construction.
All right. Well, we're just out of time now for our questions. I really want to thank you, Chuck and Cathy and Johan, for being our panelists tonight for a great discussion about how we monitor explosives and for helping put together this session. And I want to thank all of you online for watching.
So thanks, Travis, and thank you for watching this episode of the ISEE Explosives Everyday series. Explosives are the ultimate power tool that help mine the minerals and materials that are used in creating many of the products and roadways we use each and every day. They help keep our towns and cities safe from avalanches. They are used to shape and improve the environment and also in military and demolition applications. And they're in some of our favourite TV shows, movies, sporting events and concerts. Our job as professionals in the explosive industry and at the ISEE is to ensure explosives continue to be handled and applied in the safest way possible, and to continue to provide the resources and tools needed to help advance the science and art of explosive engineering. If you're interested in finding out more about the International Society of Explosive Engineers, please go to our website, isee.org. You'll find information about membership, our chapters around the world, and other useful links, including a calendar of upcoming events, as well as conferences and meetings in our industry. Another great resource is the World of Explosives, where you can find information on using explosives safely, the most frequently asked questions from homeowners about blasting, how blast vibrations affect structures, and all the planning that goes into each blast. It's also home to Explosives the Power Tool. This is a video series covering the history of explosives and the technical advancements that have been made possible because of them. To check it out, visit explosives.org. Once again, a special thank you to this episode's sponsors, LDE Global, Dyno Nobel, OPIT Blast, Sigicom and Aimone-Martin Associates, and to all our sponsors throughout this series. Before we go, here are a few short words from one of our series partners, LDE Global.
The ownership group of LDE Global has been developing, patenting and supplying explosives internationally for 50 years. In 1999, following invitations and support from international mining groups, LDE entered the North American explosives market with a range of low-density, low-shock explosives known as hybrid explosives. These are ideally suited for the huge variation of rock types and mining methods across the United States. As a completely independent supplier of explosive products, technologies, equipment and consulting services, we'd like to say thank you for watching, and feel free to call us at any time.
You have to be very quiet and gentle. You are building a new subway and you don't want anyone to notice. It's a surprise. That's why you have monitors that pick up on everything. You monitor and measure vibration, air blast, noise, dust. Nothing escapes you. You can be halfway around the world, and you still would notice every minor change here, right when it happens. People nearby don't notice anything, but you do. You make adjustments, so even less will be noticed in the next blast. What was that? A plane flying overhead? Small children playing. They're having fun. You blow up more of the rock, deep below the playground. Gently, quietly. It's a surprise after all. People appreciate you most when they can't see, hear, or feel you. The monitors show nothing, and that is everything. Infra, remote monitoring of construction sites. From Sigicom.
So that's it for this episode of Explosives Every Day. If you like this content, be sure to like and subscribe to our YouTube, Facebook and LinkedIn pages to stay up to date with all the latest ISEE happenings. And be sure to check out all 10 of our episodes highlighting the different ways explosives are used around the world every day. On behalf of the ISWE, thanks for watching and we'll see you next time.